are all here in that 8-part series. Small intestine wall there. Torso models. Looks like the big ones are over here in the corner. And now we're really using the guts. Because normally when we have used these models in the past, it was for bones, muscles, nerves, blood vessels, and we didn't need the guts to see that stuff. So now more so than the model itself, you're going to be grabbing the tubs. We have a few tubs. I'll just, as an example, bring this one up. So as far as intestines, got this piece, this one, this one. So these are actually parts of two different models, right? Slightly smaller, slightly larger. But all of this together is jejunum and ileum. Right? And then duodenum is retroperitoneal. So it's pushed up against the dorsal body wall. I don't know. Here we go. So this is the parietal peritoneum. This is the back side of it, right? So this would be pushed up against the dorsal body wall, and you can see the duodenum right there.
So it's actually outside of the serous membrane?
Correct. Yep. So the transverse colon is intraperitoneal. It's mesentery that attaches it to the dorsal body walls right here. Right? You can view it from either side. And then how about the adipose? It's a mesentery that's attached at the top, and it actually goes down and comes back up to the greater curvature of the stomach.
The greater omentum?
And that's all they're showing you of the greater omentum, just a little bit.
The lesser would be like medial, right?
Here's lesser, right? Coming off the lesser curvature, so it goes up to the liver. And here's all you're going to get for greater omentum, right? So it goes way down, curves, comes back up, and attaches to the top of the transverse colon. These models typically have little cutouts so that you can see the tunics. You can see what the surface of the mucous membrane looks like. Here you can see there are more and deeper circular folds compared to the end of the small intestine. And why would it make sense that you have more folding near the beginning than at the end? More absorption occurs at the beginning, and by the time you get to the end, there's not a whole lot left to absorb. You don't need the big surface area anymore. So would this be jejunum or ileum? Mm-hmm. Yep, and then ileum. And then this is where duodenum comes in. So this is the transition point between duodenum and jejunum. And then the duodenum is behind the parietal peritoneum right there.
Is there any functional reasons as to why duodenum is retroperitoneal?
Not that I'm aware of. Mm-mm. This provides a nice view. You can see it's kind of yellow in there where it's cut. So this is the root of the mesentery that attaches the jejunum and ileum to the dorsal body wall. So what mesentery is all of this? That's mesentery proper. Yeah. So pushed up against the dorsal body wall, ascending colon, descending colon on the sides. So they're kind of half and half. They do have a layer of serosa that covers the front, but on the back side, it's adventitia because it's just pushed up against the dorsal body wall. So they're not fully retroperitoneal, they're not fully intraperitoneal. They're neither, really. And then you have the duodenum right here, which is retroperitoneal. And then you can see the cut mesentery proper again. Duodenum on the back as well. All right, so pancreas is also retroperitoneal. Small intestine is primary site of chemical digestion and absorption. Total length of about 10 feet in the living body due to muscle tone, or about 20 feet in the cadaver without muscle tone. The duodenum itself is about 10 inches. And by the way, we're going with the cadaver lengths rather than the living body lengths. About half. So 10 inches for duodenum, 8 feet for jejunum, 12 feet for ileum. Each one about roughly half of that in the living body. Duodenum's retroperitoneal with adventitia instead of serosa, whereas jejunum and ileum are intraperitoneal. Duodenum forms a C around the pancreas, and it receives pancreatic secretions and bile through the duodenal papilla. So this little projection here is the duodenal papilla. Passing through it, bile from the common bile duct, pancreatic juice from the main pancreatic duct. And then these two fluids come together in the wall of the duodenum, and this little widened region within the wall is called the ampulla. And then you have smooth muscle around it to regulate flow through it, and thus through the papilla into the duodenum, and that's the sphincter. So you have the hepatopancreatic, hepato for the bile coming from the liver, pancreatic for the pancreatic juice coming from the pancreas, ampulla, widened region in the wall where those two fluids come together, and sphincter, which either prevents or allows those two fluids to move into the small intestine. When would it be appropriate for that sphincter to be relaxed and for those two fluids to then enter the duodenum? When there's food in the duodenum, right? Doesn't really make sense until then. And in that bile and in that pancreatic juice, lots and lots of bicarb. In fact, you're going to see 4 different sources of bicarb. Those are 2 of them. The other 2 are the intestinal glands of the duodenum, which are mucosal glands, and the duodenal glands of the duodenum, which are submucosal glands. So the 2 different glands in the duodenum, mucosal and submucosal, plus the bile, plus the pancreatic juice, 4 sources of bicarb. Because we have to get that pH from about 2 all the way up to about neutral as quickly as possible before any damage occurs to the mucous membrane. In addition to bicarb, the bile contains bile salts, which are important for emulsification of the fat that's in our food, and we'll talk about that later. And then in the pancreatic juice, in addition to bicarb, pancreatic enzymes. We have many sources of digestive enzymes. The tongue is a source of lingual lipase. Saliva is the source of salivary amylase. Stomach, gastric glands, source of pepsin. But if you're going to take any one source of enzymes and say this one secretes the biggest variety and then the greatest number of enzymes, that's the pancreas. You could argue that the pancreas is the most important organ that secretes enzymes simply because of the variety and the number of them. There are lipases. There are nucleases. There are proteases. There are carbohydrases, meaning there are enzymes to break down all 4 types of biomolecules. And when it comes to proteases, you'll see that there are many different types, 3 main different types, in fact, coming from the pancreatic juice. But all of that's covered later when we get to the fizz.
Is there a reason why the duodenum is so short? Like only 10 inches?
You know, when we give these different names, it's just to kind of break it up. So, I mean, the duodenum is really just the beginning of the small intestine, and structurally it's not all that different from what comes next, the beginning of the jejunum. It's just how somebody decided to break it up. I mean, really what you have is one thing, the small intestine, right? And there are some slight differences between what's found in the duodenum, the jejunum, the ileum, but for the most part it's just one long tube. The duodenum is known as the mixing bowl because this is where many different fluids come together. So again, from the wall of the duodenum, secretions from the intestinal glands and the duodenal glands. From the pancreas, pancreatic juice is coming in. From the liver and gallbladder, bile is coming in. And then, of course, from the stomach, which is now emptying into the duodenum, chyme is coming in. Chyme is the food stuff. So you got to mix the chyme with the intestinal juice, duodenal gland secretion, pancreatic juice, bile. Right? So that's why they call it the mixing bowl. That's where all this stuff comes together.
Is that where the most secretions happen? Did you say? 'Cause I saw
Yeah, along the intestines, yeah. The greatest number of secretions come together at that point.
just the SI in general, not the duodenum.
Well, even the duodenum specifically, yeah.
Oh, the most secretions.
Mm-hmm. And again, that's why it has the nickname the mixing bowl, where all these secretions come together. Because this portion of the small intestine is relatively short, and probably the reason why we cut it off here and said, okay, just this 10 inches is the duodenum, because this is the region that's retroperitoneal, right? And then as soon as it projects forward into the peritoneum, that would make sense to make that a dividing point and say, okay, now this is called something else. And then as you move along the jejunum, you'll see that there are lots of circular folds. There's a lot of absorption that's occurring. And then when we get towards the end, you see the circular folds become less and less abundant. The blood supply becomes less rich. So those are some structural changes that are taking place. Probably another good reason to give it a different name now. And then also in the wall of the ileum, you find some lymphatic tissues that we don't find anywhere else. What are they? Peyer's patches. So probably for these reasons, for these slight changes in anatomy, we give them different names. But that's how you're going to tell from the model series, with the 8 different models. You can tell what part of the small intestine you're looking at based on what you find in the wall. If you find submucosal glands, you know that's duodenum, because it's the only region of the small intestine that has submucosal glands. If you see big, giant lymphatic follicles, big collections of lymphatic follicles, you know you're in the ileum. Because although lymphatic follicles are found throughout all mucous membranes, they're huge and they're highly concentrated in the ileum. Those are the ones called Peyer's patches.
Is that the complete reabsorption? Or?
The Peyer's patches? Immune function, right? Lymphatic tissue, just immune function. So what comes after the ileum? And this is probably the reason why we have Peyer's patches in the ileum. That, right after it is the large intestine. And what do we have a ton of in the large intestine? Bacteria. Some of which are only meant to be in the large intestine. And to prevent them from taking over the small intestine, it makes sense that if that material was to move backwards through the ileocecal valve, which separates the large and small, and into the small, it makes sense that we have lots of lymphatic tissue there, right, to identify and eliminate the bacteria, because it's not meant to be in the small intestine. Not everyone has these, but some of us do. It's an accessory pancreatic duct, and it has its own little papilla. It's a little bit proximal to the duodenal papilla. Ileum has the abundant Peyer's patches. We've got a picture of that right here. So this is the lumen, highly folded. There's nothing in it right now, so it's collapsed. Submucosa is in here. Lamina propria over here. The Peyer's patches extend between both. They're partly in the lamina propria of the mucosa. They're partly in the submucosa. They're very, very large. And you're not going to just find one by itself. You would see that in the stomach. You would see that in jejunum or duodenum. But in ileum, they're in big collections, big groups. This is a single follicle by itself right here. And that's actually pretty similar to our intestinal wall model, the one that we used back in chapter 20 to identify that lymphatic follicle. So you can use this model for two things: the 4 basic tunics of the digestive tract, but then also more specifically, the duodenum. And again, I know this is duodenum because of the presence of the submucosal glands, here called duodenal glands. They used to call them Brunner's glands, which you'll see on the key. And then here's a lymphatic follicle by itself. So if this was ileum, you would have clusters of these all over the place. Jejunum doesn't have the Peyer's patches that you find in the ileum. Jejunum doesn't have the duodenal glands, submucosal glands, that you find in the duodenum. So that's how you're going to tell the difference between these three. If you're looking at a section of small intestine, there's no submucosal glands, no Peyer's patches, that's going to be jejunum. If you see submucosal glands, you know it's duodenum. Peyer's patches, you know it's ileum. Aside from that, they do look somewhat similar, but you do have much more folding in the jejunum than you do the ileum, since we don't do as much absorption near the end. Another look at the pancreas, accessory pancreatic duct, main pancreatic duct, tail of pancreas, body of pancreas, head of pancreas, and the duodenum forms a C around the head of the pancreas. Histology of the intestinal wall. Note there are lots of plicae circulares, circular folds, also called transverse folds. The mucosa is further organized into villi. So first level of folding, plicae circulares. Second level of folding, villi. Third level of folding, the luminal membranes of the epithelial cells that line the villi have microvilli. In all, this increases the surface area of the small intestine about 600 times what it would be if it was just smooth, right? If you didn't have any of those 3 levels of folding, you would have 600 times less surface area. With the increased surface area from all the folding, we're looking at 200 to 600 square meters. Do you remember what the surface area of the alveoli was? 100 square meters, right? Which is already pretty impressive, right? So this is 4, 5, 6 times that. The cells of the simple columnar epithelium have 2 types: absorptive cells, which are the more abundant cell type, and then scattered among them, goblet cells. Absorptive cells are called absorptive cells because their main job is absorption. That's the main function of the intestine as a whole. So that must also be the main job of the epithelial cells that line it. Because once you get across the epithelium, absorption is complete. Right? Where are you once you've crossed the epithelium? You're in the internal environment. Right? You're in the interstitial fluid of the lamina propria. And then from there, you're going to diffuse into a blood capillary, or if you're a chylomicron, the lacteal. So the blood supply and the lymphatics of the villi are going to collect all those nutrients that we've absorbed across the intestinal epithelium.
Chylomicrons are fat, right?
Yes. Under a microscope, the microvilli have this sort of fuzzy appearance, and so we get the name, it's a histological name, brush border. Later, when we get into the physiology, we'll look at the luminal membrane of the brush border and all the enzymes that are there, and they get the nickname brush border enzymes. So any enzyme that's in the luminal membrane of the absorptive cells is considered a brush border enzyme. Between the villi, you have intestinal pits, which lead into tubular exocrine glands, similar to what we saw in the stomach, except these are often called intestinal crypts. So what I was referring to simply as intestinal glands can also be called intestinal crypts because they're invaginations, right? They go straight down. This is the crypt or simply intestinal gland. And then what projects up is the villus, right? So the intestinal crypts are between villi. So you can see these little holes, right, to lead into those glands, similar to what we saw in the stomach. In fact, the only difference is in the stomach, there's no villi. But the surface otherwise looks exactly the same. Looks like it's perforated, right, with a bunch of little holes. There's a lymphatic follicle there within the lamina propria. Here's your muscularis mucosae. Once you get underneath that, you're in the submucosa. Here you can see some glands there, which must mean we're in the duodenum, and so we're going to call those duodenal glands. We have some real histology images of the villi. Here you can see there are quite a few goblet cells. Again, mucin kind of stains white or silver. And then the ones that just stain purple, those are just your absorptive cells. And then this is the lamina propria. It's just areolar connective tissue, lots of blood vessels, and of course, the central lacteal. Another villus, lacteal, running down the center. Over here, they're showing muscle fibers. These smooth muscle fibers are extensions of muscularis mucosae. And they're shown on this model right here. So when you find that smooth muscle layer, you'll see some of the fibers run all the way up into the villi. What do you think they're doing?
Secreting stuff.
It's muscle. Muscle cells contract. Muscle is for movement to move the villi. So the villi are wiggling constantly. They're always moving. The circular folds are always moving as the muscularis mucosae, that sheet of smooth muscle, contracts. Why are we constantly moving the contents within the small intestine? By moving the villi, moving the folds. What are we trying to accomplish? Along with segmentation. So this isn't for mashing and we're not really physically breaking anything down at this point. That's really been done by the time we get through the stomach. So really it's to mix the food stuff with enzymes. Constantly mix them together. Because if you have this big wad of food stuff and there aren't any enzymes in there, you're not going to get any chemical digestion. It's going to take forever to break down the food stuff. But if you're constantly mixing it with the enzymes, you're bringing the nutrients into contact with those enzymes for a much more rapid chemical digestion. So always moving, always mixing. Well, that's half of it. Once you chemically digest the nutrients, then you have to bring them into contact with what? The absorptive cell, right? You have to bring them into contact with the luminal membrane of the absorptive cell. And the constant movement accomplishes that as well, right? So mixing the nutrients with enzymes, but then once you have your absorbable units, like monosaccharides, amino acids, you got to bring those in contact with the luminal membrane to be absorbed. So it accomplishes both.
The lacteal on the last slide, is it specifically just to absorb fats?
Yes. Along with excess interstitial fluid, which is always the job of lymphatic capillaries. Aside from that, more specifically, absorb those chylomicrons. Yep, the fats. The crypts, aka intestinal glands, old name is crypts of Lieberkühn, somebody's name. Then it got switched to simply intestinal crypts. They produce about 1.8 liters of intestinal juice each day. Lining the glands, lots of enteroendocrine cells. And we're not going to give them a more specific name than that because there's a big variety of them and there's a lot of different hormones that are being secreted, whereas in the stomach it's just gastrin. So there we can call them G cells, but here it's a bunch of different hormones. As a group, these hormones are called the enterogastrones. So the enteroendocrine cells of the small intestine secrete a variety of hormones called enterogastrones. They do include a couple that we looked at when we covered the endocrine system. Do you remember what those were? So we looked at 3 that came from the gut. 1, gastrin, comes specifically from the stomach. The other 2 were specific to the small intestine. CCK, secretin. Those are 2 of the enterogastrones, and we'll be looking at their functions later. Lamina propria within the villi, rich in capillaries, lacteals, lots of lymphatic follicles, which are part of GALT, gut-associated lymphatic tissue, which of course is part of MALT, mucosa-associated lymphatic tissue. And you only have aggregates of these follicles in the ileum, and that's where we call them Peyer's patches. Capillary blood carries absorbed nutrients to the liver through the hepatic portal vein. And so the liver gets dibs on the nutrient-rich blood. Lacteals transport the absorbed lipids in the form of chylomicrons to the blood once the lymph empties into the subclavian veins. Smooth muscle contractions help move the lymph through the lacteals and mix the luminal contents in contact with the absorptive cells. So again, we're talking about the smooth muscle of the muscularis mucosae and then the fibers that extend up into the villus. They're constantly moving the villi, also creating that milking action along the lacteals. But as far as moving the villi, to mix the luminal contents and bring them into contact with the absorptive cells.
So it's both chemical digestion and absorption there. Well, it's bringing it in contact with
I know mechanical digestion gets a little gray area.
You're like moving it.
See, I consider mixing and mechanically digesting 2 different things. Now in the stomach, both are being accomplished. Right, because the food stuff is still in pretty big chunks once it's in the stomach, especially if you're like me and you only chew 3 times before you swallow.
Yeah.
So my stomach does a lot more work than my teeth. And but once the stomach has mashed and mixed and mashed and mixed, and it's now a creamy paste, that's what goes into the small intestine, and there's really not much more physical or mechanical digestion to take care of. Now it's really just chemical. But the movement accomplishes both, mixing the contents to make sure the enzymes are reaching all the nutrients, and then enhancing absorption by bringing those nutrients into contact with the absorptive cells. Submucosa of the duodenum contains numerous duodenal glands. We used to call them Brunner's glands. They secrete an alkaline mucus, and that's going to help neutralize the acidic chyme from the stomach. All right, we'll do pancreas, and then we'll stop there. So you can put a little mark next to liver. We'll pick it up there tomorrow. Pancreas has a head, a body, a tail. The duodenum surrounds the head of the pancreas. Pancreas is retroperitoneal. About 1% of the tissue is endocrine cells, organized into clusters called pancreatic islets, old name islets of Langerhans. And this is the source of insulin and glucagon, along with a few other hormones. The other 99% of the cells or tissue is exocrine in nature. And this is where the pancreatic juice comes from, the exocrine glands of the pancreas. Structurally, they are compound tubulo-alveolar glands. All of the small ducts converge, and they converge onto medium-sized ducts, and those ducts converge onto very large ducts, and eventually you end up with the main pancreatic duct and the accessory pancreatic duct. So when you're looking at the histology images, aside from the secretory units, which tend to be round, right? So you could call them alveoli, or you can call them acini. So alveolus, singular, or acinus. We usually go with acini. But aside from those, you are going to find some really small ducts, right? And these aren't the two that we just looked at. This is not the main pancreatic duct or the accessory pancreatic duct. These are the really small ducts that eventually converge to form the larger and larger ones until we get to the main pancreatic duct. Right, so these ones are really tiny. At this level, they're calling them intercalated ducts, ICDs, the really small ones, and they converge to form intralobular ducts, the medium-sized ones, ILUDs. And then from there, the large interlobar ducts, and then eventually they converge to form accessory and main pancreatic ducts. Two cell types, duct cells and acinar cells. The acinar cells form the acinus, the round secretory unit. The duct cells form the ducts. But even though the duct cells form the ducts, they do actually contribute to the pancreatic juice. All these little granules that you see here, those little vesicles called zymogen granules, they contain digestive enzymes. And a big variety of them, nucleases, carbohydrases, proteases, lipases. And it all gets emptied into the lumen of the acinus. The duct cells provide the bicarb. So the enzymes come from the acinar cells, the bicarb comes from the duct cells, it all mixes together and travels through the duct system and eventually into the duodenum. Together, the duct cells and acinar cells produce about 1 liter of pancreatic juice each day. The main pancreatic duct converges with the common bile duct, and they empty into the hepatopancreatic ampulla. So we'll go back and look at that again. And notice that the main pancreatic duct and the common bile duct each have their own sphincter, but you don't need to worry about those. The two vessels come together, empty into the wall of the duodenum, a little widened region called the ampulla. The smooth muscle around the ampulla, that's the one you need to know, called the hepatopancreatic sphincter, used to be called sphincter of Oddi. And then where the tissue projects into the lumen of the duodenum, that's the papilla. Right? So the papilla and the ampulla aren't all that different from one another. The ampulla refers to that open space within the wall. The papilla is the projection of the ampulla into the lumen of the duodenum, with the smooth muscle wrapped around it. So if you're looking at an image using a sectional view of the wall of the small intestine, that would be a good view to visualize the ampulla. But if I just show you a model where there's like a little cutout so that we can see inside of the duodenum, something like this here, we're not looking inside of the wall, we cannot see the ampulla. But if you see a little protrusion, like a little bump there, you would call that the duodenal papilla. Does that make sense? Duodenal papilla you can see from the inside, right? That little mound of tissue sticking out from the wall, but you can't see the ampulla. For that, you'd have to cut into the wall because it's inside of it.
So the ampulla is like running along with the epithelium?
I'll draw it. So you have the common bile duct and the main pancreatic duct. each emptying into this big open space, right, within the wall. But then it continues out, right? And there's like a little opening right there. So if you're just inside of the duodenum and you're looking at the wall and you see this bump here, you would simply call that the duodenal papilla rather than the ampulla. But if you can look inside of the wall, right, sectional view by cutting through the wall, then you can see the ampulla. Does that make sense?
Yeah, so it does run alongside the epithelium, because that to the left and above and below would be epithelium, right?
Yeah. So epithelium's all of this.
Are there any models that show that?
I think so.
So if you
That
go
one
down
doesn't.
into the tubule, you see the papilla, but you can't see the ampulla because it's part of the tubule.
Not tubule, but the wall of the tube, the small intestine, yeah. Where have I seen it? I'm pretty sure I've seen it somewhere. Oh, maybe it's this one. Actually, I think this one shows both because they have a cutout in the wall. Yep. So not only do they have a cutout to see inside of the duodenum, they cut through the wall itself. So you can see the part that's projecting into the lumen, the duodenal papilla, and then you can see that open space within the wall, the ampulla. So this model shows both. All right, models, have at it.